Hello and welcome to the MASTS 2025 webinar series. Today's talk is entitled Coastal Resilience in a Changing Climate, Challenges and Opportunities. I will now hand over to our speaker, who is a lecturer and Chancellor's Fellow at the University of Strathclyde, with over 15 years of research expertise in physical oceanography and coastal engineering. Please welcome Dr. Bahareh Kamranzad.
Thank you very much, Bill. Hello, everyone. I'm Bahareh from the University of Strathclyde. A brief introduction of my activity. So as Bill mentioned, I'm a Chancellor's Fellow and a lecturer at the Department of Civil and Environmental Engineering at the University of Strathclyde. I have also established coastal engineering and ocean climate research group, and I also work with Strathclyde Center for Doctoral Training in AI-based ocean forecast for marine operation. I also collaborate with Elsevier in ocean engineering and coastal engineering journals, and I'm a co-founder of the International Integrated Wave Energy Research Group. My research area, as Phil mentioned, is physical oceanography and coastal engineering and ocean climate. I'm interested in coastal hazard protection and resilience, and the more specific research areas are ocean renewable energy with a focus on wind and wave energy, climate change impacts, long-term ocean climate variability, wave modeling, including numerical modeling, self-computing methods, and extreme events. So today's presentation includes these parts. So I start with coastal ocean dynamics and how they interact or cause coastal disasters, and the climate change impact on coastal areas, the importance of ocean renewable energies, and how all of these factors will contribute to coastal resilience and have an impact on coastal areas. And I finish with providing some insight on challenges, opportunities, and the final conclusion. So we use coastal areas for different purposes. For settlement, for example, we know that around 40% of the world population lives within 100 kilometers of a coastline. We also use coastal areas for exploitation of either living or fossil resources, for the industry like shipbuilding, for trading and transport, for tourism and recreation and agriculture even, and most recently for providing green or clean or renewable energy, such as offshore wind and wave energy. So the ocean components that affect the coastal areas are categorized into four different phenomena: wind, wave, current, and water level fluctuations. So starting with wind, we have strongest wind worldwide in the latitude between 30 to 60 degrees, either in the northern or southern hemisphere, because that's where cold weather from the polar areas meets the warm weather from the equator. And then Earth's rotation will cause the strongest wind in those areas. So consequently, we have larger wave climate, which are generated by wind over the oceans in those areas. When we are talking about waves in coastal dynamics or ocean dynamics concept, basically we mean gravity waves, which have the wave periods of between 1 to 30 seconds and wave height of around a few meters. There are longer waves also which affect the coastal areas, such as tsunamis or storm surge, but we can also categorize them as water level fluctuations. So basically waves are it can be identified as sea or locally generated waves, which are the waves that have been generated due to the high wind speeds over an area in the ocean. So they are basically locally generated waves, surface waves. And when these waves travel somewhere else, which doesn't experience strong winds, they become more pronounced and their wave height reduces and the wave period increases, and they form swells. Interestingly, in areas around the equator or closer to the equator, where we have like calmer weather condition, we have the ocean or the coastal area is dominated by swells. So that's where most of the tourism attractions are also located. In real cases, in most cases, in reality, we have a combination of seas and swells. And then we have currents, which also affect the coastal areas. When talking about currents, we can both consider the really large-scale oceanic currents like Kuroshio or Gulf Stream. But when they approach the coastal area, we can divide it into two different categories. Again, we have shore parallel or longshore currents, which contribute significantly to the sediment transport. And then we have shore normal or rip currents, which act differently, and then they contribute to sediment transport from the coastal into the ocean. And then we have water level fluctuations from short-term to seasonal to long-term and to rare and extreme events like tsunamis. So each of these water level fluctuations may also contribute to coastal dynamics. So how these factors will affect the coastal dynamics? They can either cause erosion or flooding. So here is an example of erosion in a coastal areas, the Happisburgh village in England, that I'm sure many of us know about the serious problem with the coastal erosion there. So the causes of coastal erosion are either natural causes like climate change or long-term climatic changes, or human causes, for example, coastal structures or coastal protection. So coastal protection is basically designed to protect coast against erosion, but then they may cause erosion in the neighbor coast because they change the sand budget, and then the sediment transport to the neighbor coast and the coast, and they trap sand in the areas where they are designed to protect the coastal areas, but then they prevent the sand or sediment transport in the neighbor coast in the downstream. So they basically, again, cause coastal erosion. Another type of coastal disasters that we are discussing here is the flooding, and it usually happens as a result of a combination of some or all of these factors, including extreme tide, seasonal variation, storm surge, and tsunami, plus some other activities like cutting of extensive mangrove areas or extraction of groundwater will also cause coastal flooding indirectly. And then we have tsunami is another type of coastal disaster, which is not really relevant to climate change impact or climatic changes, but it's also, but is a result of either earthquake or landslides. So coastal protection, when we are talking about coastal protection, it's good to differentiate between coast protection and shore protection. So what's the difference between coast and shore? Basically, as simply we can say coast is the dry part of the coastal areas, while the shore is the wet part of coastal area. And then we have different approaches. For example, for coast protection, we can go with the soft approaches like management of the coast, like dune stabilization or cliff stabilization, or mixing of the, fixing of the coastline by structures, as you can see in these pictures. So the examples I provided in green color are some examples or some ideas for coast and shore protection using nature-based solution. The important thing is that when selecting a coast or shore or a mixed coast and shore protection scheme, we have to consider three main elements. What is exactly the problem? What we are trying to solve? Is it coastal erosion or is it flooding? And then the second is the morphological condition. What's the type of the coastal profile, the type of the coastline? Is it exposed to the oceanic condition or is it more protected? What's the type of the beach material? And finally, the land use. What's the usage of the coastal areas? Is it used for infrastructure, for example, for renewable energy, offshore energy? Is it for settlement or agriculture or other purposes? But it's also very important to consider that nearly every type of development and coastal protection along the shoreline will result in erosion of the adjacent shores and coast. Because as I mentioned, we are changing the sediment transport and removing the sand budget from the neighbor coast by protecting a special area. So moving to climate change impact, as we know, we have some global climate models or GCMs, which are also called general circulation models, that provide us with some future projections of different oceanic and atmospheric parameters. So in ocean dynamics, what we do usually is to consider a period of 20 to 30 meters of these models output in the past and in the future, and then compare them to assess the impact of climate change. So we call the historical or the past data also as present data or the control data. We sometimes use reanalysis or even like measurements like satellite data as the historical base to assess the impact of climate change by comparing them to the future projections by different scenarios. Here is just a brief explanation of the evolution of the future scenarios, the future projections and scenarios for them. So a long time ago, like around probably 2000, the first IPCC report was published, and then there were models which were called CMIP model, the couple model comparison projects, phase 3. Which provided us with some scenarios, as you can see in this figure on the right side here. So with these scenarios, which were called Special Report on Emission Scenarios or SRES scenarios, but then a newer generation of the models, the CMIP 5 models, were released with more updates on, for example, ice melting from the Arctic sheets and the projected sea level rise and their impact on future projections. And they, instead of SRES scenarios, represented the representative concentration pathways or new versions of the scenarios or RCPs. So RCPs are more reliable than SRES scenarios. And finally, the newer generation, which are called CMIP 6 models, were released in 2014, if I'm not wrong. And they replaced RCPs with SSPs, which are shared socioeconomic pathways. So it means that other factors like economic growth or education, urbanization, and other factors were also considered in these future projections. CMIP 7 models are coming very soon, perhaps, but there is no official release for them yet. So that's how we consider the impact of climate change. That was just a brief introduction of different models and different scenarios. So we all know about the energy crisis and the climate change impact that we are, and the problems that we are dealing with as a consequences of this. So the countries have been committed to net zero emissions, and a measure to do that is to use the renewable energies. But then again, we have a large populations of humans around the coastlines. So where we have access, ocean renewable energy could be a good source for providing clean and green energy. But let's take a look at the development of different types of ocean renewable energies, renewable energies, including hydropower, wind, solar, bioenergy, and geothermal. So marine energy, which is part of the ocean renewable energies, plus offshore wind, so are shown here. And as you can see, the development is still very, very small compared to other types, for example, hydropower or wind. Offshore wind is developing very fast, fortunately, but there is still lots of opportunities with marine energy to explore. This is the capacity of marine energies. I didn't consider offshore wind here because that's part of the wind energy. But focusing on the other types like tidal energy, current power, or salinity gradient, blue energy, ocean thermal energy conversion, and finally wave energy, we can see there is still huge potential with all of these different types of marine energy. Especially wave energy. Wave energy has lots of advantages compared to even offshore wind. For example, it has higher density than the offshore than the wind. So because the density of the water is larger than the density of air, of course, so it will provide some more energy with the same effort if we are able to develop a technology that can compete with offshore wind turbines. It has lower visual and environmental impacts, and it's very broad geographically, and it can add at least to the diversity of the energy mix. Plus, as well as power generation, it can be used for desalination, hydrogen production, pumping and heating purposes, and also coastal protection because it captures energy from the ocean waves. So the coastal areas behind it will probably experience less energetic waves, so less sediment transport and erosion. Plus, if we are compare them with the conventional types of coastal protection, so these technology can be easily adapted to sea level rise, which is a consequence of climate change, while some conventional types of coastal protection may not be adaptable to sea level rise. So we learned about the importance of ocean renewable energies, but climate change will affect them, and we have to consider them because, for example, climate change will change the temperature patterns, and then the wind patterns will change in the ocean, and hence the wave patterns or the wave energy will also change. So it's very important to consider the impact of climate change or climatic change or long-term trends in detecting the suitable location or suitable technologies for ocean renewable energies. Plus, unfortunately, more than 10% of the world population lives in coastal areas less than 10 meters above sea level. So in case of sea level, we have a huge impact on coastal areas in terms of flooding and erosion. Plus, as I mentioned, installation of ocean renewable energy may affect the coastal areas behind them and in the downstream as well. So it's a very complex impact, and it has to be considered as a whole. To summarize this part, climate change impact on coastal areas can be categorized into three different, areas. Climate change will cause change in atmospheric and oceanic condition, and also will cause sea level rise, and also change in extremes. So the first part, change in atmospheric and oceanic condition, will cause change in available ocean resources or ocean renewable energies. So the amount of wind power that we are estimating right now may change in the next 50 years or 100 years. Plus, installation of this ocean renewable energy will also cause coastal accretion in the coast right behind them, or coastal erosion in the downstream, because they may trap sand, or they may kind of protect the coastal areas behind them. The change in atmospheric and oceanic condition will directly also affect the coastal erosion, but in a chronic way and in the long term. Sea level rise will cause flooding in low-lying areas, and also, again, coastal erosion in the long term. Change in extremes, for example, change in the intensity or frequency of extreme events like typhoons or storms or cyclones, will also cause flooding in the coastal area. But the type of coastal erosion they cause is a little bit different. It's an acute type, and the coastal area is smart enough to recover after such kind of events in most cases. So, but still we have a coastal erosion due to the change in extreme events. So it's very important to consider the combined impact of all these factors when we are talking about coastal protection or coastal resilience and the impact of climate change in the coastal areas. So let's get a little bit deeper into some of these aspects that we have been doing some research on. So starting with the climate change impact. So I just skipped our previous research on CMIP3 models because, as I mentioned, they are a little bit old, and the scenarios are not reliable anymore. So with CMIP5 models, the newer generation of the climate models, we have done some research. For example, this figure, it shows the change in seasonal means of different parameters in the Indian Ocean. So the upper row shows the historical seasonal averages, and the lower row shows the future seasonal averages. So columns from left to right show the wind speed, wave height, swell wave height, and wave period. So as you can see, the trends in the future, according to some of CMIP5 models, are still similar. The seasonal trends will remain similar, but there is a change in average values. So in order to consider this, to detect the areas with the most stability in terms of long-term changes and also intra-annual changes like seasonal or monthly changes, we introduced a novel climate stability index, which is this one. So these MVI are monthly variability index in the future and in the historical periods. And this part, it shows the relative change in the future for each of these parameters compared to the past. So we calculated this factor for the near shore areas of the northern part of the Indian Ocean. So the higher values shows higher stability in terms of both interannual variation and also long-term climatic changes due to the climate change. So this gave us the opportunity to focus on specific locations where we found might be more suitable, for example, for exploiting ocean energy, because the situation is going to be more stable there. And then we developed higher resolution climate modeling and wave modeling actually there, which are forced by future projections from different climate models. And here you can see a higher resolution model around Madagascar and east of Africa, the historical period and the future period, the absolute change and the relative change. And again, we applied the factor we developed in the past to apply in the Indian Ocean, applied it to this region, and then again detected some areas with higher stabilities, and then continue with higher super high resolution modeling in those specific area. Here is an example of our super high resolution wave model in Reunion and Mauritius. And then we moved to CMIP 6 models using SSPs as the new scenarios. Lots of research is still ongoing, and so these are just two examples of how we try to evaluate climatic changes. Here is the historical trends of one of the CMIP 6 models, which is called MIROC 6. For the wind speed parameters, it shows long-term changes during, I think this one was, yes, for 40 years globally. And then we also use one single model, a global CMIP 6 model, another model compared to MIROC 6. It's a little bit different, so it's called ECR3. And use a single forcing with multiple wave characteristics just to see how modeling will impact, or the modeling tool will impact the results of our future wave projections. And that was very interesting because different model will generate a little bit different results, and it showed the importance of considering the uncertainties in wave modeling and the tools that we are using. And then for ocean renewable energies, we also try to consider both intraannual variability and long-term changes in detecting the suitable areas for wave energy in this case, which hasn't been considered. A lot of research and report on wind energy, wave energy, available resources detect the suitable locations only based on the amount of energy available in those areas. But we have to consider the climate change impact, or at least long-term climatic impacts, to make sure that the energy is stable, at least for a while in those areas. Here is an example of considering both intraannual variability and technical consideration. It's a little bit old, but this was the first time we considered this in detecting the suitable locations. And then we later expanded this research with having access to longer term atmospheric data to be able to generate longer term 60 years of wave data globally. So with that, we could develop a global wave model and then develop a new factor which gave us the areas, which identified the areas with higher amount of energy and lower monthly variability as an indicator of intraannual variability, and areas with lower rate of change during 60 years. So we want areas which have more wave energy, more available wave energy, and lower intraannual variability and lower long-term changes. So this factor that we developed enabled us to detect those areas globally. We apply that on a local scale here. Here is an example of applying that factor that we developed around Japan that showed us the areas with larger potential for stable wave energy. We again added that technical consideration with some development of devices, new devices, which were added to our information over the time by developing these new technologies, and then also made some recommendations for how to select the suitable location and the suitable technology considering the climate change impacts. And added to that, the geographical consideration of the location where we are applying this methodology. Here is an example of a research we did in South China Sea. So we had to go through like anything like water depths, distance to coast, because that's a very complex area to work on, lots of islands, and we have Taiwan banks there, which are the giant sand waves between Taiwan and China. So we have to consider a lot of factors when we were trying to detect the suitable locations. And about extremes, here again, we use the Indian Ocean wave projections, but this time for the extreme events. So here you can see the historical change of seasonal maximum wind speed, wave height, swell wave height, wave period, and also the wave power. And this is the future and how the seasonal values will change in the future. So it's very important to consider the change in extremes as well, even in detecting the suitable locations for ocean renewable energy technology. Here are also some examples on a more regional scale. So again, this is Madagascar and east of Africa, and this is the change in so this is the changing, this is the historical maximum significant wave height in different seasons, and this is the historical maximum wave period in different seasons. So the maximum are drastically changing in different, on a seasonal scale as well. So we try to find a relationship between the change in different parameters, which was very interesting because even the relationship is changing depending on the location or depending on the scenario that we are using for the future, or depending on the model we are using, for example, for wave modeling. Another example, we also worked on the change in the frequency of extremes and its impact on ocean renewable energies. Here you can see an intra-annual variation of the wind speed. The events where the wind speed is larger than 6 meters per second and its corresponding wave height, which were wave heights of larger than 4 meters. We chose this 4 meters because this is the cutoff wave height for several of wave energy converters or wave energy technologies. So that was really interesting to see how the frequency of extreme events also change in a specific location, and if we can actually find a relationship between them. Finally, we also worked on extreme value analysis. That was a very interesting study because we used the 60 years of data that we generated on a global scale for extreme value analysis to detect the extremes that we may get in a specific return period, which was 100 years here. And we show that depending on the source of the data, we may get different results. The satellite data here are giving us very lower values for the extreme value analysis because of the gap in the data set and also the spatial and temporal resolution, which was very lower compared to other resources. So the left panel is our the results of our modeling, which we actually did the simulation for 60 years based on a Japanese model called JRA55 and using a wave model called SWAN. And the panel in the middle is ERA5, the ECMWF product. So it's very important to choose the right source for all the analysis when we are trying to capture the extreme events in different locations. It's also important to choose the right time span. So if our results show that it's really important if we consider the longer term data set, because then we may be able to capture the climatic impacts as well. So there are challenges in this type of research. As I mentioned, some of them, we have uncertainties in ocean simulation and resource assessments. Different wave models, for example, generate different results. Or, if we have 10% error in our output, in our input, for example, in the wind characteristics of an input to a wave model, that will generate 20% error in the outputs. So we should find a solution to address that. There are also uncertainties due to climate change, because obviously we don't know what's going on in the future, and what's going on now that may affect the future. So we have different scenarios. All of them have the possibilities to occur. And then when it comes to certain types of ocean renewable energies, there is a discussion about their efficiency and LCOE. For example, wave energy has still a very large LCOE compared to offshore wind, for example. So it doesn't really justify using that despite having a great potential. But that means that there are also opportunities to address these challenges. For example, for the first part, we can develop high-resolution regional and local simulations and downscaling both characteristics, both input and outputs of any model. Here, for example, wind and wave. And also we can work on wave model development. For the second one, we can use the multi-model ensembles or develop regional climate models, which, for example, in the UK, we have to some extent the UK City 18, or applying some data assimilation methods. For the last part, we can use the combined wind and wave energy, for example, working on the co-location of different types of energy sources, just to, that can use the same infrastructure to reduce the LCOE for that combination. And also we can work on the multi-purpose usage of these ocean renewable energies, for example, coastal protection, as I mentioned, because they affect the ocean dynamics and hence the coastal areas behind them. And on the top of all of that, we can think of working on application of AI as a new tool, or as a replacement of all the numerical modelings, which are very time consuming, very expensive in some cases. And if we can address all these uncertainties, or at least reduce them using AI. So to summarize, we talked about the complex impact of climate change, which have to be considered in the coastal areas. And it's important to consider that nearly every type of development and coastal protection along a shoreline will result in erosion of the downstream coast. And the source of the data will affect the reliability of the estimates. So have to choose the best possible option, and the period of data analysis also affects the outcomes. But challenges also present opportunities for in-depth research in those areas. These are the list of some of the collaborative institutions where we generated this research in different subjects like climate change or ocean renewable energies or even extremes. And these are the list of references, and that's all. Thank you very much.